talk about my favorite mission that's close to the sun. So I'm going to tell you what's up with the sun, some recent results from NASA's Parker Solar Probe. So a little bit about myself. I have worked in lab, as Cece was saying, for about 20 years now. This is me inspecting one of the mirrors in the sounding rocket. This is a sounding rocket that we launched out of the desert in 2012 in New Mexico. And then worked with a variety of other NASA satellites. We have Hinode solar satellite, which is collaboration with JAXA, worked a little bit on Hubble data, Chandra data, as well as this atmospheric imaging assembly, which is pictures of the sun every 10 seconds. These groups, this is some of the people that I work with. So science, again, is never done alone. These are just a few of my many colleagues that I've had the honor to work with over these years. So other things about me is I love the beach. So I definitely crave my beach time and looking forward to summer. I'm a yoga instructor and a yoga teacher on the side. And I love cupcakes. And I also have a cat who you might see wander through every once in a while. So that's a little bit about me. So returning to those beaches that I love so much. So this is one of those things that the sun gives to us, is that the sun is important because it sets the temperature at the Earth along with the atmosphere, that we're able to have liquid water. And we're also able to have this warmth, and it's something that we've adapted to and are able to thrive on this planet. Unlike others that are too hot, such as Mercury or Venus, or too cold, like Mars or Neptune or further out. Another thing that the sun does is to create this beautiful aurora. So as the sun creates space weather that travels to the Earth and interacts with our atmosphere, and that activity shows up as northern lights. And the northern lights, or southern lights, depending on where you are, tend to focus on the poles. So you have to be kind of north to see these things, and they're beautiful dancing sheets. If you ever get the chance to take a trip to see them, I highly recommend it. I was lucky enough to see them in Michigan during the last solar maximum, or 2 solar maximums ago, and they were just absolutely incredible sights to see, very mesmerizing to watch. So when we look at the sun, kind of with our plain eye, and again, we never look directly into the sun with our own eyes, because that will damage them. But if we safely look at it through the right filter and a telescope, we see a relatively yellow ball with only this black spot here, or maybe a couple of spots, depending on the time. And those are sunspots, and those are the centers of magnetic activity, and kind of gave the first clues that the sun was magnetic. Now, we didn't have to wait till the space age in order to actually understand this. Drawings from as early as I think this is 1130 AD, or Common Era, is there were drawings of the sun with spots on them, and that magnetic characteristic was recognized. These were drawn in 1873 of a sunspot. So you see these beautiful tendrils of plasma and gas focused in, and then darker areas here with more concentrated material that you were able to draw basically from looking at, again, a safe telescope. So enter the space age, and we were able to actually take pictures of the sun. So what we did is we used an occulter. This is an occulter disk. The sun would be the size of the white circle. We blocked out the sun around it, and we see this constant flow, these explosions that we were talking about, coronal mass ejections, billions of tons of material coming at us at millions of miles an hour, equivalent to what would be 80 million school buses. So this is a lot of mass being hurled out in all directions, as well as this constant flow of solar wind from the sun. And so those eruptions are here, and this is just about a quarter of the sun, and this is the approximate size of the Earth. So we also see how little the Earth is compared to these large structures, these large, huge explosions, these temper tantrums that the sun throws. So this is something that can not only affect the Earth, and again, the Earth is not this close to the sun. This is just for scale, but it's something that we need to think about. as we become we further explore the solar system. So Parker Solar Probe was 60 years in the making. And we're doing it because we're explorers. And there's this practical matter of living with a star, as I was talking about, with all those coronal mass ejections and flares, huge magnetic explosions, and then also scientific curiosity. So Parker Solar Probe was first proposed by the Simpson Committee of the Space Science Board in 1958. And that was the same committee recommendation that was to found NASA. So the question goes back to the very beginnings of NASA. And looking at those space weather drivers, there are 3 space weather drivers that we talk about, is the flares coming off the sun. Again, those huge explosions that, if you kind of bottled up that energy, would run the US power grid for 80,000 years. The coronal mass ejections, these billions of tons of material, all those school buses that are racing towards us. And then energetic particles, which are the fastest things that would be the first messengers that come and interact with our Earth and its atmosphere and help create that aurora. So other things that space weather can affect on the Earth, besides just the gorgeous aurora, in some ways you would think that would be a bonus that the sun gives us and helps tourism in the North. However, it can also do things like damage satellite spacecraft electronics. It could harm astronauts if they're out on spacewalks. It also disturbs the ionosphere, which is used for a lot of communications and GPS signal. So in terms of that, we really rely now on our GPS and on those types of communication. So that's important for us to understand when these things, when the storms are going on in the sun and how they're going to affect the Earth and our technology here. It can also induce ground currents that can wreak havoc on power grids. And doing that, it could black out cities, which again would be catastrophic. So we're trying to really understand how this all works. So the other reason why we do Parker Solar Probe is a scientific curiosity. So the sun is mysterious, and it does at least 2 very weird things that we're trying to still figure out. So the first of which is, in the center is the heat source of the sun that actually is creating a fusion, pushing atoms together to make energy and releasing energy in the process. So that's its campfire in the center of the sun. And as you go away from that center, it gets colder. That yellow disk that I showed you is around 5,000 degrees from the 15 million in the center. And then as you go out to its atmosphere, to that which hangs around that yellow disk, it goes back up to 1 million degrees. So there's some heating process that as you've walked away from your campfire, you've actually gotten hotter, which is not something that we experience here on Earth. So that's one of the scientific curiosities we went to go investigate. And this is, again, the sun is hotter here, cooler here, and then the atmosphere again gets up to millions of degrees. So we have a couple of theories of how this works, and the images on the left, the movies that are playing, are taken by that atmospheric imaging assembly, and we're watching the sun's plasma or gas, very hot gas, dance and churn and move, especially this row kind of right along the center. So this is a cartoon of what we think happens, that it heats as the magnetic fields are being shook along the surface. And then this movie on the right shows that those explosions, a flare happening here, so those large amount of energy releases in this explosion could happen by rubbing of magnetic fields, and in that explosion then sending off plasma. So we went closer to investigate to see which one could possibly be heating the corona. Now, how are we going closer? That was Parker launching from the Earth and now going in again and again to the sun and then back out. It'll interact with Venus from time to time and actually push itself closer and closer. And so that's why we need to make sure that the planets were actually aligned so that we could use Venus 7 times to push ourselves closer and closer into the center, towards the center of the sun at 9.86 solar radii from the sun. So that's 96% of the way there. And once we're there, we had to make a model of what we wanted to do. And sometimes you use what you have left over at lunch. But we knew we needed to measure the temperature because we were worried about what was warm. Something like an anemometer, so figuring out which is the wind direction and all that stuff blowing off at. We wanted to talk about the magnetic field, since I've mentioned magnetic fields multiple times. And then we always want to take a picture of where we go whenever we do explore. So those were the basis of why, of things that we wanted to take with us, or instruments that we needed to build in order to successfully meet our scientific objectives. And the part that I was most involved with was the solar wind electron, alphas and protons instrument suite, which is the SWEEP suite. And this solar probe cup peaks around the heat shield. This heat shield right here protects most of the spacecraft from the sun and keeps it at just about a little under room temperature for most of the time, a little bit cooler sometimes, even to the point where we need heaters when we're actually at closest approach on the back end, because there's no other heat except for the sun. And when you block it all out up here, there's nothing going on the back, but the cup pokes around the side to actually sample the gas directly. And then we have two other analyzers on either side. This is actually a liquid cooled system. So these are liquid water radiators behind the heat shield. These are our solar arrays. And then a magnetic thing. And this is our phone for home, our phone home device, or our satellite dish to talk to high gain antenna to talk to the Earth and send back data. So what SWEEP measures is the speed, the density, and the temperature of the solar wind. So how much of it there is all of the area under the curve. We're adding up how many particles we have. The temperature is about how wide they are, and the velocity is where they peak. The number of them are peaked. So we can get hydrogen and helium, and we can also do electrons. So this is an image of the actual cup just before it was integrated into the spacecraft. And we couldn't use things like aluminum. So we instead had to use things like tungsten, molybdenum, niobium, titanium, and sapphire, because these will survive the temperatures that this cup has undergone and will undergone. So the sapphire is actually in here. It's not the typical blue that you would see in a gemstone, but a white of a lab-made sapphire. And we can't use epoxy. We do sometimes glue things down so screws don't shake loose upon rocket launch, because rocket launches shake things a lot and we don't want things to fall out. So instead there's these braided wires twisted together and these very, very small screws that are really hard to see, let alone also tie down. And so everything is safety wired. We couldn't also use normal testing facilities because they just didn't go up to those temperatures. So this is IMAX film projectors that, instead of being projected out, are actually refocused in, and a couple of them together can recreate the sun. Focus back in here, can recreate the sun on the cup that's hiding in the vacuum chamber. We did a lot of tests to make sure that we were going to be able to survive and proceed with mission. This is testing the solar panel. So this purple light is testing each row to make sure that it's going to get the right amount. It's going to be able to react and generate the power that we need as we're on our 7-year mission. And this was the picture on top of the rocket. So this is the Delta, part of the Delta IV Heavy down here. And this is the fairing. The yellow grid is the fairing that closes around it. And the Faraday cup is up top here with the heat shield up here, and the other parts of SWEEP are down here as well. So again, this is a large team that pulls this all together. There were the scientists and engineers that put together the cup and was placed on this just before it was placed on the spacecraft. There are some of the launch vehicle folks, all these scientists and more. And unfortunately, Dr. Gene Parker, who the satellite was named after, had passed away in the last week or so. And he was a very great man, very persistent, very kind, and really just had a huge effect on all of us. But there are so many more folks who are studying this and who are benefiting from all of his brilliance. So some of the things that we found, one of the things that our camera Whisper was able to take a picture of was Comet Nusoi, which was unexpected that we came across that. Then there was Venus. So originally we were not slated to turn on around Venus, but we found that we were able to. So the camera came on and snapped this picture. And what's special about this picture is actually seeing for the first time from space the cloud cover. And then this matching of the radar that was shown in previous missions to Venus with the white light or visible light that Whisper is able to see. And they match very, very well in terms of what's going on the surface. So this was a really great discovery that we just did not think we were going to have, but Parker was able to deliver. The next thing was going to talk about is meteorites. So meteorites, you sometimes see it streaking through the sky. And you know, there are still questions there. And so although Parker does not have a dedicated dust detector, it was able to really look at the dust cloud, the zodiacal dust cloud that has fragments, and that due to the sun's pressure, these beta meteorites sometimes escape the solar system due to the fact that they're being flung out. And so Parker is traveling through some of these and is taking measurements and able to measure between the camera actually seeing them, as well as the electric field antennas registering an electrical signal from them. So as they collide, there's these other ones that go away from their orbit. And so they were actually able to create this picture of what's happening from Parker Solar Probe data. So again, we didn't originally go in there, and this was another surprise about where these exactly, where they're coming from, as well as where they're going in terms of these meteorites that are being formed throughout the solar system. So another very interesting result is the coronal mass ejection. So this is a complementary satellite, part of the Heliophysics System Observatory. The stereo satellite took a picture of the sun in November of 2018 and a few images together, and it looks relatively benign. There is some activity, there looks like there's some things throwing off, but nothing very drastic. When you do a running difference, if you're looking to this side, you start to see that there was actually a coronal mass ejection. So a running difference means you're subtracting one image from the next so that you're getting the difference between the two. So you can more easily see what the coronal mass ejection is doing, or what the sun's corona and solar wind are doing. So this is a baby picture that only a scientist can love. This is what the sweep in the particle and fields data looks like for that coronal mass ejection. And the coronal mass ejection specifically is between the two dotted lines. So you have time on the bottom, and as time goes on, you get different blips based on the temperature, the density, the velocity, and the magnetic fields. And this change in magnetic field is one of the indications that you have this, as well as the changes in velocity and the temperature. So this was the first coronal mass ejection that Parker saw very close to the sun, the closest ever observed to the sun. And it was slower and a little different than what we normally observe out at Earth. So this was a new discovery as to watching the coronal mass ejections as they're first released from the sun. So looking at what's next, coming up in June, so a few months from now, we'll go into perihelion 12. So each time we come close to the sun, it's a perihelion. We have 26 total. We're at number 12 in June. And then in September, same distance, we'll do it again, December, and on until August of 23, where we'll do another Venus flyby. And every time we do a Venus flyby, Parker breaks her own record, speed and distance record as the fastest human-made object, as well as the closest to the sun. So there'll be another step in closer to the sun. There will be a few orbits. Then November 2024, it'll be the final Venus flyby. And again, breaking her own speed and distance record, going as close to the sun as the mission can do. And then on perihelion 26 in December of 2025 will be the last of the nominal part of the mission for Parker, and touching the atmosphere again, and getting a feel for what's happening there.